Okay, this is where I was hoping to get to yesterday, and I don't think we got to this slide and saw it at all yesterday, did we? Did you write this down?
No.
This table right here that's in the end of the book, the title of it is Standard Reduction Potentials. That word standard shouldn't be overlooked. It's really important in this case. Anytime you have a standard reduction potential, it's going to have the degree sign on it. It's going to be epsilon naught. This is epsilon, and then that sign is called naught. What that means is, for anything that's aqueous in here, it's got to be a concentration of 1 molarity. And anything that is gas has to be 1 atmosphere. So if you have a cell and you don't have those concentrations, then the cell potential you get from this thing is not going to be accurate. And for those that one watching on YouTube, this is in the end of the book, page 825. This is the reduction potential table. And this last bullet point is going to be disturbing to you. I'm going to warn you right off the bat.
You used the right effect. Oh my god.
I always do.
See, I see so many teachers and they just don't get it right. Isn't effect is
When I said I always do, I don't know if that's true. I probably don't.
you used it right.
I didn't know if you caught me before using it, so I thought you were looking for an argument. So
No,
I
I was
didn't
just-
give it to you.
Noticing that one teacher got it right.
I'm not even sure if that is the right effect.
It is.
I always think of affect with an A as emotional, like
No.
affective.
It has nothing to do with that.
Yes, it does.
Affect is a verb. Affect is a verb. You're affecting something. Effect is the noun. Like it's like,
So it's like
what happens.
I think you're
It's a
wrong.
thing.
Look it up.
We're right. I'm
I
pretty
mean,
right.
effect with an E can be a verb.
Well, it
Prakya.
can, but it can, but it's not.
Take a
like-
rock.
Yeah. Well, it can, but like it's.
Oh,
not
so it can.
It can. It's like
Oh, so it
affecting
can.
the change,
Okay.
like something like that. It can be like that.
Affecting something.
No, it's like really can be.
Hey, we want to do things right. Every class is English class.
British English.
Does that work for you?
Why do we have to change the English? Like British English and here.
Oh,
Why
stop.
can't they be same? I write center as RE still. Not ER. Center. Like British people do center for us.
Yeah.
I still do.
Yes, ma'am.
No, racist is not that. You don't know the definition of racist.
So what's what? This thing right here. I'll show you what I mean. If we have iron plus 2 with 2 electrons added going to Fe. This is on the reduction potential table. It's below hydrogen. It's around halfway down in the right column. The reduction potential for that is negative 0.44 volts. What bullet point 3 says is if I have to multiply this half reaction through by 2 so that the whole reaction balances out, then I just multiply 2 by 2. 2 Fe plus 4 electrons yields 2 Fe's. My new reduction potential is still 0.44. That's what I said would be disturbing. Because you're not used to that, are you? Wheeler, go ahead.
Why would you times it?
Oh, if your thing, so this is a reduction. If your thing that was oxidizing was taking in 4 electrons, was giving off 4 electrons, then the electrons have to be equal. So you may have to multiply a half reaction. This is just a half reaction. That's not quite consistent with Hess's law, is it?
No.
Nick?
Is that because you have a different current, different voltage? Would the current be different?
No, here's why. Because this standard reduction potential, what does it say? Standard reduction potential means that all your solution concentrations are 1 molarity. So whether there's a 1 in front of your solution or a 2 in front of your reactant, yeah, it's still 1 molarity, and that does not change the reduction potential. That's why. Okay? So this goes against Hess's law. It goes against the manipulating the K values for equilibrium. Remember, for K, if we multiply 3 by 2, we square the K. Now, we have a third scenario where we have reduction and oxidation potentials. You multiply through, you don't change the potential. Sir?
Is that only for standard?
Yeah, that's the only time we're going to use these values is for standard. If we have non-standard conditions, we will have some formula that we'll use. But the table values are just for standard and yes.
So we're never going to have like just E reduction without those circumstances?
You will have, let's see. No, you won't have E reduction or E oxidation without a naught sign. However, you will have E cell without a naught sign because together they may be non-standard.
And then that's when the formula comes in and we're not going to see.
Yes, that's right. When you have both the oxidation and the reduction together. All right, so let's move on. What I'm saying here is this table that I just gave you, this is only good for standard conditions. That means all solutions, even the products have to be, you don't start with 0 products in this case, you start with 1 molarity of products. That's kind of weird too. You have to start with products, reactants and products. And we'll talk more about that. It takes a little while to say everything that we need to say before you can start understanding everything. So I'm hoping that we can get to a point where you think, oh, okay, I kind of get that. And we may not, though. So a complete description of cell is going to have 5 components to it. I have number 5 on the next slide.
Oh, wow.
Try to keep it real quiet so only I can hear it if anybody and when it's totally quiet in here. Why is it so quiet in here?
It's Friday and it's been a long. Yeah. It's peaceful, isn't it?
I was just yanking the chain of the girl to watch this on YouTube.
She's gonna sit there and be like, ah, no.
If you're down at the last number 4, I'll talk more about number 4, but I know even though we don't have platinum in here, you're welcome to always use platinum on paper. It is a very good electrode to use if a non-reacting electrode is needed. You can use graphite if you want to on paper, but you just say PT.
What if we manage
That'll
to
work.
find platinum for the cell of the lab?
it's not really going to help very much because it's more about the things that are reacting. Platinum wouldn't react. So to illustrate what's going on in number 4, what I'm trying to say, your description should say what your anode electrode is. The electrode is the bar of metal that's in there that's connected to the wire. Both compartments need to have a bar of metal. If the anode or the cathode has a metal as a reactant or product, then use that metal for your electrode. If it doesn't, then use platinum. That's what I'm saying here. But you can hear it when we actually start drawing these things, though. It's going to make more sense or be more useful to us. Are we done writing all that? I thought you were just being spiteful saying no, Sean. You wouldn't do that, would you?
I would never do
Thank you,
that.
No place for that in chemistry, is there? The last thing about a complete description of a cell, I'm going to move this up a little bit, is something that we use in electrochemistry. You've never seen this before. It's called line notation. And it's just another way of expressing what a cell contains with the chemical equation. So you can have a cell made up of an iron-copper system where you have copper reducing in the cathode, iron oxidizing in the anode. What was that? At the anode, something is oxidizing. Who's oxidizing in that reaction? Right. Fe is changing to Fe plus 2. I'm going to leave the electrons out of this thing to show what we have here. And at the cathode, we have the reduction of copper ions to neutral copper. Notice both of these half reactions have a metal. The metal is going to serve as the electrode for both of these compartments. So at the anode, you're going to have a bar of iron in there attached to a wire that has copper at the other end of it. That's what's going to have over here. Doesn't matter that iron's a reactant here and copper's a product there. Just make sure that your electrodes are metal bars. Another way to write this chemical equation in terms of what's going on in the cell is to do it like this. This gets a little confusing for people. Now I'm showing you a simple one first. Now you don't have to identify what the anode is and what the cathode is. I'm telling you now, but from now on you just have to know the anode is always written first and the cathode is always written second. You do them in alphabetical order. This represents the salt bridge in between the anode and the cathode. Okay? So you're always going to have the two lines separating the anode from the cathode. Yes, sir? I'll ask you, give the line notation for this reaction. For instance, next week on Friday in the battery lab, I'm going to ask you, sketch your cell and write the line notation for the reaction that occurs. And you should be able to know what's reacting and what it's making for both sides. Yeah?
So if we have like an inert metal that's like
Like platinum or whatever?
Yeah, so do you just not write that line?
Yeah, the answer is no, you need to write it in there. And because every time you use line notation, you must say, my board is off some. There. Make that exaggerated. That has to be the electrode in the anode. That must be the electrode in the cathode. So if you do have platinum, you're going to put platinum over here. And we'll have to then do something different if it's not reacting in here. I'll show you what that is in a moment. Again, this is a simple system because your electrodes are actually reacting. either being reacted or being produced.